Okay, so we're starting chapter 3.2, and we're talking about the empirical rule for symmetrical distribution in z-scores. And next we're also going to speak about if a data value is unusual. The empirical rule is a rough guideline for approximating that percentage of data within 1 to 3 standard deviation. 1 to 3 standard deviations. 1 to 3 standard deviations of the mean. And here's the key: unimodal and symmetric distributions only. Important that the distribution be unimodal and symmetric. And this is the guideline. 68% of the data is in 1 standard deviation, 95% is in 2 standard deviation, and almost all of the data is within 3 standard deviations. So I want to show you what this looks like. If I were to draw a picture of this on a graph, and I have some distribution going that way, what this is saying is that if the mean is located here, then the first set of data, 68% will be located in that region. Within 1 standard deviation. 2 standard deviation would contain 95%, less or more than the mean, will contain 95%, and then the rest of the data within 3 standard deviations. 3 standard deviations away. So these were the guidelines that are used to determine roughly where the data is located. Here's an example. Data on smog levels in a sample of cities was collected, and the distribution was found to be roughly symmetric and unimodal. This is given, okay, roughly symmetric and modal. The mean for the particular sample is 10.7 micrograms per cubic, and the standard deviation is 2.6. So the mean is 10.7 and the standard deviation is 2.6. So this is, for this region, is 10.7 minus 2.6, and 10.7 plus 2.6. That's 1 standard deviation, contains 68% of the data. And then 2 standard deviations would be 10.7 plus 2 times 2.6, and 10.7 minus 2 times 2.6. That would contain 95% of the data. And then if we went 3 standard deviations out, that would be nearly all of the data. 3 times the standard deviation, or 10.7 plus 3 times the standard deviation, would take us all the way out to the end of the spectrum. Okay, so that kind of shows how that works. In other words, about 68% of the cities will have smog levels between 8.1 and 13. About 95% will be 5.5 to 15.9, and about 2.9 will be all the data. And please notice the standard deviation is 2.6. That's already given. Okay. Another example, the empirical rule for temperatures. The mean daily high temperature in San Francisco is 65 degrees with a standard deviation of 8. So find the temperature ranges for 68, 95, and 99.7. Use the empirical rule. So we're given the mean and we're given the standard deviation. The mean plus or minus the standard deviation is for 68% of the data. The mean plus or minus 2 times the standard deviation would be 95% of the data. And the mean plus or minus 3 standard deviations would be the 99.7% of the data. Since 95, now this just breaks down everything that we're saying, so I'm not going to read all of that to you. Okay. Finally, in this section, we're going to talk about something called z-scores. A z-score measures how many standard deviation observed data value is from the mean. For example, a z-score of 1.5 means the observed data is 1.5 standard deviations above or below the mean. So sometimes it's not possible to get exactly 1 or 2, so we might go to 1.5 or minus 1.5 and so on. A z-score of 1.5 means the observed data value is 1.5 below the standard mean. So by default, right, by default, a z-score a z-score of 0 would mean what? Think about that for a second. What would that mean if the z-score was 0? Okay, so if you said that the observation is equal to the mean, the observed data is equal to the mean, in other words, it hasn't moved from the mean, is exactly equal to the mean, then that would be the correct answer. To compute the z-score, 1 second, z-scores allow us to compare observations in different distributions. Now, let's look at how to compute the z-score. Road A, known facts, so this is data about 2 drivers traveling at 70 miles an hour. Driving road A is relatively faster. So here, road A is 60 miles an hour, road B is 60 miles per hour, but the standard deviation is 5 in the first case, 10 in the driver on road A is traveling relatively faster since 70 miles an hour is 2 standard deviations above the mean, while it's only 1 standard above in the second case, this case. So you can use it to compare what's happening. Easy computation for z-scores. The distance from the mean, this is the formula you will use, the distance from the mean divided by the standard deviation to compute the z-score. So that would be the number you're given minus the mean divided by the standard deviation. For example, Maria scored 80 out of 100 on her first stats test in a course and 85 out of 100 in her second stats exam. On the first exam, the mean was 70, the standard deviation was 10. Second example, the mean was 80, the standard deviation of. In which exam did Maria perform better? So in the first exam, we can compute the z-score. She got 80, the mean was 70, the standard deviation was 10. In the second exam, she got 85, the mean was 80, the standard deviation was 5. So Maria scored one deviation above average on both exams, so she did equally well on both exams when compared to the whole class. Okay, so we can't really make a claim that she did better on one exam, and although she scored higher on the second exam, because of the mean, students generally scored higher on that exam anyway. Okay. All right, now let's look at some of the homework problems. Questions 1 to 5 on the homework are actually from the notes. I'm not going to talk about them. Here's a question I just answered for you. If an observation has a z-score, this means that it is equal. The observation is equal to the mean, and so on. Okay. Which of the following can be used to compare measures in different units, such as inches and pounds? So remember that z-scores can be used to compare across different types of data. All right, now let's talk about the problems here. So in 2011, the mean rate of violent crime per 100,000 people for 24 particular states was 440. The standard deviation was 150. Okay, so mean is 440, standard deviation is 150. They're telling us to assume that it's unimodal and symmetric. Now, here's a graph showing the different parts of the data that's given right there. They're actually worked it out for us. And notice the first one standard deviation is at 68%. So the question is relatively straightforward. Remember, after two standard deviations, the mean would be 95%. Okay? Remember the rule, 68 to 95, 68%, then 95%, then 99.7%. Okay? So how was the number 590 on the graph obtained? So think about this, okay? To get 590 is equal to 440 plus 150, which is, this is one standard deviation. So by adding one standard deviation, okay, mean plus one standard deviation to give 590. What are the crime rates for cities A, B, and C? So city A is two standard deviations. So city A is 440 minus 2 times 150. 440 minus 2 times 150, two standard deviations right there, which is what? 440 minus 300 is 140. The crime rate for city B is one standard deviation, which is 440 minus 1 times 150, which is 290. And the crime rate for city C is 440 plus 2 standard deviations, which is 440 plus 300, or 740. So we've found out that at city B, it was 290. Remember, this is 95% of the data here. That's 95%. At city B, we just calculated it to be two. Oh, it's asking about 2 standard deviations. So city A is at 140, and at city C is at 740. So that, am I looking at that correctly? Oh, I'm sorry, it's one standard deviation, not 2. Within 1 standard deviation. No, I'm sorry, it is 2. Would you expect to find 95% of the crime rates? So I did read that incorrectly. All right, so 140, 290. So that would be within 2 standard deviations, which we computed as 140 and wasn't it 740? Yeah, 140 and 740 between the 2 standard deviations out. We already computed that from up here, right? From 740 and from 140, A and C. Then would you expect for 1 standard deviation, B was at 290, and in this city, 1 standard deviation is at 590. So 290 to 590, right? $290 to $590. The question continues. If one of these states had a violent crime rate of 445 crimes, would this be considered unusual? Clearly, it would not be considered unusual because it's within 1 standard deviation. Okay, it is within 1 standard deviation because that's 440. 1 standard deviation is between 440 to 590, right there. And 445 falls between 440 and 90, so it would not be considered usual because it falls within 1 standard deviation. And then the last part of this is 103 crimes. Would that be considered unusual? So remember what's happening with our table here. The furthest one here is 140, and this is 790. 103 falls way off to the right. So that will be way off to the right somewhere. That would be very unusual. It falls below 140. So yes, 103 would definitely be considered highly unusual because more than 2 standard deviations below the mean. Okay, probably 99.9 or something like that. Continuing. So this is question 7 on your homework. In 2007, the mean rate of violent crimes per 1,000, similar question, right? In 1,000 people per 10 regions in a certain was 350. So mean is equal to 350. Okay, remember that's X bar, and standard deviation is 112. Using the empirical rule, what 2 values would you expect to find 95% of the data? So for part A, 95% of the data would be 350 plus 2 times 112, and 350 minus 2 times 112. Two sets of data, which is, if we compute it, is 126 and 574. Okay, 126 and 524. 574, so 126 and 574. Now, this is a different problem. It says in another region, the crime rate of 430, would this be considered unusual? Oh, wait, I'm sorry, I didn't do the second part. %68. So that's part B is 68%, which is 350 plus 112, which is 230. I'm sorry, this, I think I've got this mixed up. This is 574. Yes, I did. I have the numbers backwards, but I think you guys figured that by now. This is 574, and this is 126. Okay. In this case, it's 350 minus 112, which is 238, and then 350 plus 112, which is 462. When you're entering it, please enter the smaller one first, the one to the left first, and then the one to the right. All right, so let's make a comparison. If in this region we have 430 crimes committed, that would clearly not be unusual, right? Because 430 falls within, remember, one standard deviation is between 238 to 462, okay? And 430 falls in here, in between here. So it's not unusual because it falls within one standard deviation. Now, in another region, 77 crimes per month, that would be very unusual because it's way below two standard deviations. Remember, the two standard deviations is 126 to 574, and 77 is a number that's way lower than 126, so that's way below two standard deviations. Next question is asking us to, in 2007, the mean property crime rate for the 24 states west of a certain river was 3,309, and the standard deviation was 706. So mean is 3,309, standard deviation is 706. What percentage of the states would you expect crime rates to be between 2603 and 4015? So we have to do a little bit of work here. Let's see what happens with one standard deviation. 68%, 3309 plus 706, and 33. Let's do the minus first. 3309 minus 706, and 3309 plus 706. And if we put those in your calculator, go ahead and break out my calculator again. We get 3309 minus 706 is equal to 2603, and plus is 4015. So this is clearly one standard deviation, or 68%. Now let's check 95%. 3309 minus 2 times 706, and 3309 plus 2 times 706. And if we put that in the calculator, we get 1897 and 4721, which is clearly 95%. If someone guessed that the property crime rate west in one state uh, west of the Mississippi was 9046, would this be consistent with the data? So let's see what 3 standard deviations would be. If we did 3 standard deviations, okay, 99.7, 3309 minus 3 times 706, and 3309 plus 3 times 706, we get 3309 minus 3 times 706 is equal to 1191, and then 3309 plus 3 times 706 gives 5427. So clearly, 3 standard deviations from the mean is 5427, the upper bound. Okay, the upper bound. So clearly 9046 is way above that. So clearly it's not going to fall within 3 standard deviations. It's well above 3 standard deviations, well above, and it is therefore unlikely that a state would have this value. The dot plot shows heights of college women. The mean is 64 and the standard deviation is 3 inches. Complete parts A and B below. So what is the z-score for a height of 73 inches? So z-score, z for 73 inches is equal to 73 minus 64 divided by 3. Which is equal to 9 over 3, which is equal to 3. So the z-score for 73 inches is 3. Okay. Remember your formula, z x is equal to x minus x bar over s. So that's part A. Part B, what is the height of a woman with a z-score of -1? So given z x is equal to -1, x bar is equal to 64, and s is equal to 3. Let's write our formula. Zx is equal to x minus x bar over s, and substitute what we know. So we know that zx is -1 is equal to x minus 64 over 3. And I'm sure you guys can solve this. Multiply both sides by 3. We get -3 is equal to x minus 64. And then add 64 to both sides. We get x is equal to 61. Okay. I'm expecting you guys can solve this very easily, no problem. Basic algebra. One final question in this section. An IQ test has a mean of 108 and a standard deviation of 10. Another one has, which is more unusual, an IQ of 98 or 123. So let's check Z for 98 first. That's 98 minus 108 over 10. Okay, so 98 minus 108 is negative 10 divided by 10, which is negative 1. Then for 123, it's 123 minus 108 over 10, which is 15 over 10, which is 1.5. So clearly an IQ of 123 is more unusual because the corresponding z-score is at 1.5, is further than from 0 than negative 1. Okay, if you think about the number line, 1 to 1.5 will be somewhere about here, but to negative 1, so the distance to 1.5 is much more to the right. So 1.5 would be more unusual, or 123. All right, chapter 3.3 is not, there's very little computation to do here. I'm just going to walk you through some of it. The questions are mostly definition questions. So we're talking about the median, something called the median, and the interquartile range. The median is the middle number when the data has been sorted from smallest to largest. Okay? So there's one definition for you, that if you sort the data from smallest to largest, you have the median. To find the median, arrange all the numbers in order and find the middle number. If the two numbers are in the middle, average them. Think of the median as a middle point, and this is a good measure of typical value for skewed distribution. Remember how we can't use the mean? You know, the mean is a good measure for data that is not skewed, that is uniform. But if the data is skewed, then the median is a better measure. Here's an example. Remember this example from chapter 3.1 with the gas prices at different pumps? Well, if we were to arrange this data from least to greatest, okay, we would see that the middle numbers are between 2.9 and 2.99. So we take the average of that and we get 2.99. The median price of 1 gallon of gas at these stations in Austin was 2.99 on the particular day. Now, recall that the mean was actually um, 2. The mean was actually 3.02, which is slightly different from the median, which is 2.99. I want to also show you how to find the median using the TI-84 calculator. So we would go to our calculator, go to stats, edit your list, and type in the numbers that we have for the data. Remember how to clear this. Go up to L1, clear, enter, and then start entering your data for the different gas prices, which is 2.93, 2.95, 2.95, 2.97, 2.99, 2.99 again, 3.09, 3.09 again, 3.09 again, and 3.19. Now, press that again, calculate one variable statistics, and all you do now is take this arrow down to the median, okay, to the median right there, 2.99. Remember, this value was let's just put these two in the data. The mean value was 3.04, but if you scroll down to MED, you get the median value of the data. Okay, so capture this screen, put it into the data, into the notes for us, just in case you want to go back and look at it again. There it is. Okay, and that's where that 2.99 answer came from. That's up here, the 2.99 right there. Now, just as a discussion, we talk about how to measure spread. The standard deviation measured from spread using distance from the mean. We use something called interquartile range. To understand interquartile range, we need to first talk about what the range is. The range is the difference between the largest and the smallest values. Okay? And we're going to talk about interquartile range in a little bit. The group of 8 children have the following heights, and they're listed here. The smallest number is 48, the largest is 71. If we subtract the two, we have the range. Now, if we were to do a dot plot of this data, put all of this data on a dot plot, we would have a dot plot. This looks like this. And if we were to divide the dot plot into quarters, each quartile contains 25% of the data. So the dots in the first quartile are 25% total of the number of dots, 25% of the number of dots, 25% of the number of dots, and 25%. So 25% of the weight are between 101 and 121, as in the first quartile, and so on. Okay. What the interquartile range tells us, the range of the middle 50% of the data. Okay, the range of the middle 50% of the data, which is between 160 and 121, or 39 pounds. So, if you were to put this data into the TI-84 calculator, let's go ahead and find the interquartile range for this data here. So I'm going to go ahead and put this data into a calculator. 48, 48. I'm going to have to write this down. Okay. 48, 48, 53, 53.5, 54, 60, 62, and 71. Okay, and we'll go ahead and put this into my calculator in a list. So I'm going to use that same list, edit it, clear it, and I'm going to put in the new data that I have, which is 48, 48, 53, 53.5, 54, 60, 62, and 71. Okay, then I'm going to go ahead and press stats again, calculate, and you want to just scroll down a little bit to see into quartile range 1 and into quartile range 3. So you see quartile 3 and quartile 1 is 50. So there's my data, and I can see quartile 1 and quartile 3. So the interquartile range is Q3 minus Q1, which is 61 minus 50, or 10.5 range. This means that the interquartile range of the heights of the 8 children is 10.5 inches. All right, your homework for this section, starting at question, we already did question 10. Starting at question 11 is from the notes. There is, I don't believe, any calculation for this section. You should be able to answer the questions from your notes. I'm going to do every other one here for you. So the value will be right in the middle, would be the median. The median is often used when data is skewed. The interquartile range tells us the middle 50% of the data. What about question 16? Maybe I can try to help you with question 16 here. Okay. Question 16, name the 2 typical measures of a center of distribution and under which each is preferred. So under what conditions is the median preferred? Oh, I'm sorry. What the 2 measures of the center of distribution would be the mean and the median. Okay. That's the 2 things we talked about. The median is preferred when the data is strongly skewed or has outliers, and the mean is preferred when the data is symmetric. This came from the notes for 3.1, 3.2, 3.3. Question 17, name 2 measures of the variation and state the conditions under which Each measure is preferred for measuring the variability of a single set of data. So, hint, this has to do with interquartile range. Interquartile range. Okay. So your answer would relate to the interquartile range, and think about when you would use the interquartile range. Okay. And then the second, if the data is skewed, and then remember that we use the standard deviation when the data is symmetric. So think about which two answers you'd want to pick here. And I can see the answers, but I'm not giving them to you. Okay? But standard deviation is used when the data is symmetric, and interquartile range is used when the data is strongly skewed. All right, I think that's all we have to talk about here.